When we talk about reflection, we usually mean reflecting across a line or axis like this one here. Reflecting a shape, like the letter F, means looking at the mirror image on the other side of the axis. So here's the reflection of the letter F across this vertical axis. Next, take a look at these three shapes here. Which has been correctly reflected across the axis? Right, only this ellipse down here was reflected correctly. To reflect this triangle, it should have been flipped around. And to reflect this green arrow across the axis, it should have been over here instead. Next, let's look at reflecting points on the coordinate plane. So first off, select the point 2, 3. Great, so here's 2, 3. Now if you were to reflect this point across the x-axis, select the resulting point. Exactly, if you reflect 2, 3 across the x-axis, you wind up at 2, -3. In general, if you reflect the point A, B across the x-axis, where do you wind up? Exactly, when you reflect across the x-axis, you should multiply the y-coordinate by -1. So if you were to reflect the point -3, -4 across the x-axis, what are the resulting coordinates? So next, try reflecting the point 2, 3 across the y-axis. Select the resulting point. Exactly, you wind up at -2, 3. So in general, if you reflect the point A, B across the y-axis, what are the resulting coordinates? Right, so when you reflect across the y-axis, you multiply the x-coordinate by -1. Now, in addition to reflecting across lines, you can also reflect across points. For example, you can reflect 1, 4 across the origin, which is the point 0, 0. After that reflection, we wind up over here at -1, -4. So next, try reflecting the point -4, 3 across the origin. Select the resulting point. Nicely done! So reflecting -4, 3 across the origin, you wind up at 4, -3. So in general, if you reflect the point A, B across the origin, where do you wind up? Excellent! Now, you can also reflect across lines other than the x and y axes. For example, let's sketch in the line y = x. If you were to reflect the point 5, 1 across this line, you'd wind up over here. So what are the coordinates of this resulting point? Right, this point is 1, 5. So in general, if you reflect the point A, B across the line y = x, what are the resulting coordinates? Nicely done. So finally, suppose you were to reflect the point -2, 3 across the line y = -1, which is this line down here. What are the resulting coordinates? So to summarize, if you start at the point A, B and you reflect it across the x-axis, you wind up at A, -b. So you flip the sign of the y-coordinate. And if you reflect across the y-axis, you flip the sign of the x-coordinate, so that's -a, b. Reflecting across the origin means you should flip both signs, so the resulting point is -a, b. And reflecting across the line y = x means you should swap the x and y coordinates. Don't worry about memorizing all these rules. You should be able to quickly rederive them by drawing a sketch for yourself with a few coordinates. In this lesson, we'll talk about stretching. Suppose you have a square and you stretch it in this direction. What shape do you have now? Exactly, you get a rectangle. Next, let's start with a circle, and suppose you again stretch it in this direction. What shape do you have now? Precisely, so a stretched circle is an oval or an ellipse. Now suppose we were to stretch this shape again, but this time in the downward direction. So now we stretched it by equal amounts in two perpendicular directions, meaning this is a 90-degree angle over here. So what shape do we have now? Exactly, we have a circle again. and it happens to be a bigger circle than the one we started with. So now let's define the term dilation. Dilation is when you stretch something by the same amount in two perpendicular directions. That's a complicated definition. The simpler definition is that a dilation changes the size but not the overall shape. So if we started with a circle and then we dilated it, we would get another circle. To get this specific circle, we had to stretch the smaller one by a factor of 2 in the horizontal and vertical directions. So this scale factor is 2. Now suppose you have a rectangle over here and you dilate it to get this larger rectangle. What would you guess is the scale factor for this dilation? How much in each direction would you have to stretch the smaller rectangle to get the larger one? Exactly, the scale factor for this dilation is 3. So next, we'll be looking at dilations on the coordinate plane. Now before we dilate anything, go ahead and select the point 2, 3. Okay, now let's dilate. Here's how you write a dilation in the coordinate plane. So for any point x, y, you're moving it to 2x, 2y. So for this dilation, you're doubling the x-coordinate and the y-coordinate. So what are the resulting coordinates after this dilation? Well, doubling the x-coordinate of 2 gives us 4, and doubling the y-coordinate of 3 gives us 6. So we've dilated this point to 4, 6. Now if you apply this same dilation, multiplying the x and y coordinates by 2 to the point -2, 3, what are the resulting coordinates? Right, so -2, 3 becomes -4, 6. Now suppose we had a rectangle defined by these 4 points. After this dilation, doubling all the x-coordinates and all the y-coordinates, sure enough, we wind up with this larger rectangle. So now you can see how this coordinate transformation is actually a dilation, and the scale factor is 2. The larger rectangle is twice as long in each direction as the smaller rectangle. Next, let's try another dilation. Suppose you have the point 2, 5, and you're applying the dilation x, y to 1/2 x, 1/2 y. So now you're multiplying the x and y coordinates by 1/2. What are the resulting coordinates? Well, half of 2 is 1, so that's the new x-coordinate, and half of 5 is 2.5, or 2.5. So after this dilation, the coordinates are 1, 2.5. Next, suppose you apply the dilation x, y to 2/3 x, 2/3 y to the point -6, -3. What are the resulting coordinates? Exactly, the new coordinates are -4, -2. And if you apply this dilation to all the points that make up this rectangle, you wind up with this smaller rectangle. So what would you say is the dilation factor of this transformation? Right, this dilation factor was 2/3. So dilation factors that are greater than 1 make shapes bigger, while dilation factors less than 1 make shapes smaller.